Hello everyone, and welcome to Understanding Physics, in which you will try to understand physics and try to gain certain concepts through the way that I explain things. So, so we want to talk about motion in 2 dimensions and 3 dimensions, which is one part of kinematics that we have done on the last chapter, but now we are going to be doing this in 2 dimension as well as 3 dimension. And so the way that you need to describe certain things will be much more different compared to one-dimensional, but then you could bring those one-dimensional case into the two or three-dimensional case. So so first to start up this entire thing, we need to talk about what is a vector, because we have already explained certain variables to be a scalar or a vector, but we didn't really define what a vector truly is. So what is a vector? So a vector is a mathematical symbol in which it has a starting point and a finishing point. And this is what we call as a vector, as it goes from point A to point B. Or sometimes we could write this as AB vector, or if you define this to be a vector like that, we could call it as a vector like that. So the way that you actually add vectors up is very simple if you do it geometrically or if you do it algebraically. So let's just discuss the geometric way first. So let's say you are in a coordinate system, and let's say you have a vector going in this direction and a vector going in this direction. Let's say this is A and this is B. So we want to talk about addition of vectors. So let's say we want to add vector A and vector B. So how do we define this? So the way that we will do this is that you will first draw your first vector, vector A, and then you will put the tail of the second vector on the head. This is like basically stating that I want to move from this origin point to a certain point, and then moving another certain distance. And so you you will move a total of A vector plus B vector, which you can do that by looking at your millimeter block. And so you could also define scalar multiplication, which is a way for you to write to do scaling of the vectors. So let's say if you have a vector and then you want to do this 2 times of a vector, this is the same thing as stating this to be a vector plus a vector. So this means that I will go in this direction once and then going in here another time. So you can see here that the length actually doubles. So basically what this means is that you are doubling the length of the vector. And so with this, we could actually do this algebraically as well. And the way that we will do this algebraically is that we need to know that every single vector can be decomposed into vectors into n independent vectors, which we will call the unit vectors. So let's just state that if you are in a 2D coordinate system and you have vector A here, you could always decompose it into addition of a vector going horizontal as well as vector going vertical. And let's just take this to be the x and the y. So we could write this as the I hat direction and the j hat direction. So what does this hat mean? This hat means that it is a unit vector. And the way that we would actually describe this is that a unit vector will have a length of 1. And then another property of these unit vectors, which we will actually define here, is that if we use a coordinate unit vector, they will all be perpendicular with each other. So let's say I hat will be perpendicular to j hat. So basically they are within 90 degrees of each other. So if this is I, this will be j. And and you could also do this with three-dimensional vectors as well. So so normally if you do things in 3 dimensions, you normally follow something called the right hand law. So basically if this is I and this is j, this would normally be k. So so if you put your index in this direction, let's just try to draw this nicely. You put your index in this direction, and then you will put your middle finger into this direction. So this will be your other fingers, and this will be where your thumb will be. I know the drawing is not that good. So yeah, this will be the thumb, index, and the middle. And this is the way for you to define coordinate system in a three-dimensional case. And you would also notice that each of these are perpendicular with each other. And so this is what we mean as a n-dimensional space, where basically it has three perpendicular vectors, which like yeah basically means that you cannot really uh, define. Oh, sorry. You cannot define one of the vectors from the other vectors, and this is what makes dimensions really important for you to study. And yeah, it will basically discuss about how you actually uh, decompose different vectors together. So let's just go back to our definitions. So yeah, let's say you have a vector A going in this direction, and and it is moved I hat here and j hat here. And let's say here you got a length of about 2 and then the length here about 1. So yeah, I haven't really discussed about how you measure the length of a vector, but yeah, the way that you could do this in physics is that you would just measure it with a ruler. But yeah, there are like certain trigonometry that yeah you could use to actually to define what the length of each. But yeah, I will later try to discuss it through the problems as well. So so yeah, let's say vector A is something like this. So we could actually define the vector A to be I hat plus 2j hat, or sometimes I normally write it as 1, 2. And so if you actually do addition, addition is very easy for you to do. So let's say vector B will be 2I hat plus j hat. So this will be 2, 1. So if you add A vector and B vector together, you would get a 2, 1 plus a 1, 2. And so adding vectors together is very easy. You just need to follow the top one, add it by the top, and the bottom add it by the bottom. Same thing with 3 dimensions, but then yeah, instead you have 3 different variables. So this is quite simple. And what about multiplication? Let's say 2a vector. So you could write it as 2 times 2, 1, or basically this is the same thing as 2 times 2, which is 4, and 2 times 1, which is 2. And this is how easy vectors is. And yeah, even if you multiply it with a negative value, this will always work. So yeah, anyways, if you do addition or subtraction, the rules are always the same. And so now we could define what is truly a distance as well as displacement and as well as position. So let's start by defining those. So let's say if you are in a coordinate system and you move from point A to point B, starting from point 0. So what is position? So position is the way for you to define where you are located from this from this origin point. And this is what you call as the position. So in here, we could say that the position of A will be at a certain coordinate, or you could also define it with a vector. So you need to go in that direction to go into that position. And so what is distance? So let's say if you move from point 0 to point A, and then you move from point A to point B, the distance will be the length of this added by the length of this. So basically it is depending on your path towards there. So let's say if you go from point 0 to point B, if you if you move something like this compared to this one has a higher distance compared to the nearer one. And so what is displacement? So so you start from the origin and then you go to this place B, even though even though you travel something like this, but basically your change is only from this point to this point. And so and so the displacement is only the change in your position. And so writing this not only as zero, but yeah, using A or like yeah C, that is like your displacement, while your position is from a one I- is only from one reference frame. So that's the way of me describing vectors. And and so some and so there are some important things for you to know in manipulating vectors, which is the trigonometry. So let's say if I have a vector from one place to another, and 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 I know this to be a certain length, let's say 2. You could uh, you can find each of the components in the x and the y direction if you know the angle here, which I will call theta. So yeah, let me just write the length to be the modulus of A, which is basically the symbol for the length. So let's just actually first try to define how many I-hats do I need to travel to go in this direction. So if you actually look at this diagram, you could see that you need you need uh let's just do it like this. Uh, the component AX, compare that with the length of A, is basically the definition of cosine theta. So you could state this to be AX to be the length of A cosine theta. And so this is how many I-hats you need to go to that vector A. And you could do the same thing for AY, which is the AY over the A of the modulus of A to be sine of theta. So you would know that AY is the length of A sine theta. And so you could figure out that you could write things in modulus of A cosine theta I hat plus the modulus of A sine theta j hat. And yeah, this is a way for you to actually to write things down using only the length as well as the angle. And so how do you actually convert from this into the other state? Well, it might be a little bit tricky, so let's just state this to be AX I hat and AY j hat. And 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 if we see this case, we could figure out what is the length of this only by knowing each of these components. So yeah, if you actually look at the AX and the AY, you can see that this is a Pythagorean theorem, which is basically the length of A squared is AX squared plus A squared of Y. So basically you know the length of A to be the square root of ax squared plus ay squared. So this is a good information for you to know, while the other information that you need will be to figure out what the angle is. And so the way that you could actually figure out the angle is that if you compare ay and ax, you could figure out this to be the tangent of theta. So that means that the theta is the arctangent of ay over ax. And so and so this this and this are important for you to use to write vectors. Moving on to the second part, we want to talk about velocity as well as acceleration. But we will do this in terms of vectors. So, last time in a one-dimensional case, we only care if it is going in a positive direction or in a negative direction. In here, we cannot really define what is positive and what is negative, but yeah, instead we could actually define in what direction it is going at. And so this is one of the important things that you need to know, is that velocity and acceleration are vector units. That means that they have direction, unlike speed, which is a scalar. And yeah, basically the speed is the length of the velocity. So we could write first that the average velocity is delta r over delta t. Well, what is this r hat? No, sorry. What is this r vector? This r vector resembles your position, and so what is the average velocity? It is the change of position over the change of time, and the same thing as before. If you actually set this to be the instantaneous velocity, you would figure out this to be the limit of delta t going to 0 of delta r hat over delta t. And this is basically dr hat over dt. And this is the definition of velocity, which is the same thing as what we got from the previous chapter. And we can do this with acceleration as well, which is the change of v over the change of time, and the instantaneous acceleration, or the acceleration itself, is the limit as delta t goes to 0 of delta v hat over delta t, which is basically dv hat over dt, which is the same thing as d squared over dt squared r hat. So you can now define what is the velocity and the acceleration vectors for a certain movement in space. So now we want to talk a little bit about what is relative motion. So we need to remember certain cases, like we cannot truly know our velocity because everything is relative. So let's say if you are running, and then there's a train going at a certain speed while you're moving at with another speed. Well, you would feel that the train moves slower compared if you stand still. And so this is one of the key components in what is relative motion, and this question is brought up again in relativity, in which you discuss if the object moves at a very high speed, which might distort your perception of time as well. So the way that we will try to define relative motion will be if you have, let's say if you are in a let's say you are in a plane, and there's one object, there is another object, as well as there's another object right over there, And let's say this is the object that you want to try to observe, and this is the first reference point, and this will be the second reference point. So, first of all, what I want to do is that I want to define what is the position of this object compared to the second reference frame. Let's just actually do this from the first reference frame. So yeah, we want to find the position of the object with the reference frame of the first reference frame. And you would figure this out. No, sorry. And so you could define what the position is just by drawing this vector here, and you could probably compute this. You could also compute this as well. Let's just actually remove the coordinate there. So this is the position of the object with relative of the first reference frame. And we could also define what is the position of the object from the second reference frame. So we will define this to be x02. And so how would you define x02 by using x01? Well, you would also need one other reference frame, which will be from here to here, which is basically the position of the first reference frame from the second reference frame, and we will state that to be x12. And if you see this, you could see that x02, the vector, is basically x01 vector plus the x12 vector. So okay, this is just simple geometry in which that you could figure out what is the position of the object compared to another object. But now we want to think about what about its velocity. Well, we can actually figure this out. So let's just actually take the let's just take the derivative of each, and yeah, note that this change in position over the change of time will be the velocity of the object with reference of the second frame, and that is equal to the velocity of the object from the first reference frame and the movement of the reference frame depending on each other. And so this is one of the important formulas in relative motion, and this could actually describe certain things that you might see, such as for example if you have a plane and it moves at a certain speed relative to the wind. So yeah, let's say this is the speed relative to the wind, and you would know the speed of the wind to be, let's say for example, in that direction, the velocity of the wind compared to the ground. You could figure out what is the velocity of the airplane with respect to the ground, and this is one important part in relativity, which is we couldn't really tell what is the true velocity of a object. We could know the velocity depending on our reference frame, and so this is one of the key concepts that I want you to focus on. So after that, we want to talk about a very interesting case of motion in 2 dimension, which is when it has constant acceleration, which is the same thing as like last time. You could you could use the same formulas to define the positions, but now I want to do this in a much more specific way. So let's say let's say if you have a object being let's say if you have an object being fired with a certain angle, and then there is only gravitational acceleration going down, how would you actually describe this movement of particle? And this is one of the most specific case of constant acceleration, which is what we call as projectile motion. So, for the formula of the constant acceleration, we would always know the formula to be the a vector over 2 t squared plus the v vector t v vector 0 t plus the initial position, the r0. And this is what you define as the r vector with respect to time. And so if you want to try to solve this for the projectile motion, we can just do this straight away just by only plugging in the values. So let's just actually do this step by step. So we have our acceleration vector to be, so yeah, let's just state our coordinate system, I hat and j hat. We figure out that the a vector is sorry, there is only one acceleration, which is only going down. So there won't be any change in the speed in the x direction, but there will be a change in the y direction, which is going downwards. And so we can write this as 0 and negative g. And that's the acceleration. So what about our initial velocities? So we can write this down as by decomposing the vectors. So the one going to the right, that will be v0 of cosine theta, while the one going up will be v0 sine theta. And then we can also figure out what's the initial r0, which will be the x0 and the y0. But to simplify our case, let's just set x0 to be 0. Why? Because we want to simplify our lives. So we want to set x0 to be 0. But then why not y0 to be 0 as well? Well, have you ever think about a condition in which if you actually fire this from a building and then it will later hit the ground? If we define this to be 0, we would need to figure out this change in height. So the best way for me to do this is to actually to say this to be y0 and this would be 0, as it will be much more easier to model. So we already have the entire equations, so we can figure out what is the position only through using this one formula. So we could write x to be, it will be let's just start from the r0 and then working our way back. So it will be 0 v0 t cosine theta and then another 0. Okay, and then the y will be y0 plus v0 t sine theta, and then there's the negative g over 2 oh, what's the sign? Yeah, t squared. Okay, so we got this in terms of time, but then we would also notice that we could actually substitute time in x, because if you know at what time you are measuring it, you would know at what position would it be, and vice versa. So let's just actually try to get what time is, and let's just remove time from this equation straight away. So we will figure out the time to be x over v0 cosine theta. So if you check the unit, this will be length, and the bottom will be length over second. And so the entire unit will be seconds, so it will make sense. And let's just try to plug this in here. So if we try to plug in this time inside this y, we'll be able to obtain y0 plus x tangent theta minus g over 2 v0 squared second squared theta. Multiply that by x squared. And this seems to be a very weird case for us to write, but this makes sense since we can see this to be a parabolic motion. And so we want to also try to figure out one thing which is very specific, which is the y0. So, no, sorry, the range of the x. And we'll do this with a simple assumption that the y0 here is 0. So this will actually simplify our computations. So we want to figure out what's the maximum distance and as well as the angle that we need to get the furthest distance. So if we actually look at this straight away, if we want to obtain the next 0, therefore we need to figure out that 0 would equal to x of tangent theta minus g over 2 v0 squared cosine squared of theta. Well, so yeah, basically the top and the bottom is the same thing, x squared. So we can first factorize the x out because basically our solution couldn't be 0 anyways. So we could just divide them all by x because x is not 0 in this case. So after that, we could try to move things out. So we could write x equals to tangent of theta, multiply that by 2v0 squared cosine squared of theta over g. So this might seem to be a jump, but the way that I see this is that I would move this to the left hand side and then multiply each side by 2v0 squared cosine squared theta over g. And this would obtain v0 squared sine 2 theta over g. So basically sine 2 theta is sine theta from here and cosine theta here, and then where's the over cosine theta and where's the other cosine theta? They cancel each other out. So this is our range. This is our horizontal range for this projectile. And so now we could also try to ask, what is the maximum for this range? So if we want to try to figure out what the maximum of this range, we could do it only through observing the property of this function, instead of us doing this analytically. So we know sine theta to be a function of something like this. So we know a maximum to be 1 or negative 1. But we want to try to figure out the maximum, therefore we can just assume this to be 1. So we know that the maximum would be v0 squared over g, which is the best case scenario. And then not only that, we could also know when this will hit this 1, which is basically when sine 2 theta is 1, which is basically when 2 theta is pi over 2. So this would be pi over 4. At theta to be pi over 4. So This would mean that you need to shoot it at a 45-degree angle to get this maximum range. And this is where the knowledge of you need to shoot something 45 degrees to get its fullest range, and this is true based on the mathematics. So we could actually look at this in a simulation that I have already set up. So in here you can see there are lots of different parameters, but in this case we want to set the y0 to be 0, which is our case. And then in here we could just change the theta however we want it. And these two are functions of the position. One of them is a linear one, the other one is a parabolic, but I won't actually display this. Instead, I want you to actually look at the simulation here. So you can see here that if you shoot it with a certain speed, it will go from one place to the other. And if you try to figure out what is the speed horizontally, you can see that it is actually moving at a constant speed. Compare it moving up and down. We could also see this by lowering the angle. We could see that this guy moves almost straight, while in the vertical direction we could see it to be accelerating and yeah, decelerating as well. And so to find this maximum distance, we could just play around with this angle, but if we set this up to be pi over 4, we figured this out to be the maximum point, which is the v0 squared over g. And so we could also think from the formula that v0 squared over g must be its maximum. Therefore, if you increase the gravitational acceleration, the range will shorten out. So yeah, if you actually increase this out, you can see there are some changes, but then if you shoot this, for example, at the moon, you can see that the range would go further and further. Even though that I didn't change the theta p, this will always be the maximum no matter in what gravitational acceleration that yeah, you are in. And then you could also fire the thing with much more speed or not, but it will be the same thing regardless of the v0 and the g. So basically pi over 4 is the best that we can do to shoot it horizontally if we are on the flat ground. But maybe there's a question like, if you are at a certain height, what is the angle that you need to shoot in order for it to go in a much more further distance? And this is a very interesting question. And the way that you could actually solve this is just by setting this to be y0, and then you could just play around again with the angles. And so yeah, in here we figure it out to be something else, but feel free to actually to do the mathematics and try to derive what's the longest range for a case in which you change its initial height. So let's get back to our topic in discussing the topics that we need to cover. So there's only one last thing that I want to cover, which is the uniform circular motion. This is one of the hardest things for you to do in mathematics, but you can actually do this very simply. You can do this very simply through the geometry. So what does it mean to have a uniform circular motion? So basically you are spinning in a circle and you have a constant speed. not a constant velocity. So, the way that you would actually derive the motion in a circular orbit, so the way for you to derive a motion in a circular orbit is through a little bit a little bit of geometry. So, let's say you start from one position and then you move to another position, and here this will be theta r. Okay? And let's just state to be there's a certain angle right over there. We could also model its change in velocity here, and there's a very small gap in the change of velocity, right? And here's the thing. These two are proportional with one and another. Therefore, I could conclude that the velocity over the radius would be the same as the change of velocity over the change of radius. No, sorry, the change in position. So, we have figured this out. So, we could actually do something very interesting, which is if we write v over r, multiply that by the change in r to be delta v, but then we divide it by the change of time, we get something very interesting. If you take this limit of theta t going to 0, we would be able to obtain the v squared over r, which is equal to the acceleration. And this is only through the mathematics. We didn't do any physics. This is always true if you move something around in a circle at a certain always at the same speed. So we figured this out to be v squared over r, which is a, and checking the dimensions, this will always be true. And technically this is wrong. This is technically the length of v squared over the length of r as the length of a. So where is this acceleration going towards? Well, if we actually look at this graph, we could just see that the velocity actually goes inwards towards the circle. So yeah, in here this is the change of v. So that means that the acceleration should also go in this direction, which is towards the circle. So basically this is the acceleration's direction. And so this is the way for you to model a spinning system, only by using its velocity and as well as its acceleration. So if you are already given the velocity as well as the radius of the circle, you could figure out what's the acceleration towards the center of the circle, which we normally call as the centripetal force. So that's all for this lecture. I hope this is not as confusing, but I hope this will help you in your journey into understanding physics much more. So thank you very much, and I will see you guys later on.